So this is what a typical M&R spectrum is going to look like. There are four things we'll be looking at. One will be the number of signals, because that tells us the number of different kinds of protons that are present. In the compound above, there are 4 different types of protons. The location of the signal will tell us about the local environment of those protons. The area under each of the peaks is going to tell us the number of that kind of proton. And the shape is going to tell us about the number of neighboring protons. So let's start with looking at the number of signals. The number of signals is going to tell us the number of different kinds of protons that we have in our compound. So we're going to need to identify the different kinds of protons. And we're going to want to find ones that are equivalent. So chemically equivalent protons occupy identical electronic environments. And they produce one signal. These protons may either be homotopic, or they might be enantotropic. They are not diastereotopic. Okay, so how do we tell whether 2 protons are homeotopic or an enterotopic or diastereotopic? First, homotopic. Let's go back to our green. I like green. Okay, so these are chemically equivalent protons. They can be exchanged by rotational symmetry. So to do this test, to tell whether something's homotopic, we can do a replacement test. We draw the compound twice, and replace one of the protons with deuterium each time. If the compounds are the same, they're homeotropic. So we can look here, if you rotate this compound, it's the same as that. These are the same. And so that is a homeotopic compound. Let's look at another compound. Let's look at ethanol. So here's our ethanol. Let's move it up on the compound, move it up a little bit. So here's ethanol. And we've got proton here, and we've got, we're going to draw it twice, and we're going to deuterium here. And I'm sorry, let me fix that. I'm going to make them different. Okay. If we rotate this, we do not get, they're not interchangeable. but they are intertropic. And so they are chemically equivalent. And they are chemically equivalent. Because we have a plane of symmetry. If we put a plane right in here, so that it's with this piece of paper and these bonds are on the plane, there's a plane of symmetry there. And so these two, if we make that a hydrogen, would be chemically equivalent. Let's look at some other examples. We look at chlorine or fluorine, and then we've got two hydrogens. These are going to be enantiomers of each other if we do the replacement test. And that's because we can draw a plane. There is a plane of symmetry here. They're not homeotopic because you can't rotate one into the other, but these are enantiomers. They're reflectional. If you put a mirror here, you get a reflectional image. Distereotopic protons are not going to be chemically equivalent, and the replacement test will lead to a diastereomer. So if we do the replacement test here, we get a hydrogen on the top here, and now we've got a deuterium down there, and we get the deuterium coming toward us here, and the hydrogen going away, and we're going to leave the hydroxy in the same position. Okay, so what we've got here are two chiral centers. There's one here and there's one here. And this one is identical to the first one here is identical, but this one is switched. The second one is switched. And so that makes these two diastereomers. So these two positions are not chemically equivalent. And you should get two peaks on your NMR spectrum. So let's look at this guy and see if we can determine if he is homeotopic, enantotopic, or not related. So if we take him and we rotate it, we get something that looks like this. So that's not the same. We can't do a reflectional. There's not a pane, not a thing of a reflection there, so we can't reflect it. If we do the replacement test, we get the hydrogen there, or we put the deuterium here, or we can put the deuterium up here and put the hydrogen down here. These are diastereomers. So let's determine whether these the two protons in red are homeotopic and entotopic or not related. And what we're going to do here mostly is just look for planes of symmetry. There's a plane of symmetry there, so these are going to be homotopic. There is not a plane of symmetry here on B, and so these will be enantiomers. And these will be different chemically. Again, here, there's no plane of symmetry. And they will be in entotropic. Okay, here we have a plane of symmetry, and so these are going to be homotopic. Here we make two enantiomers. If we replace one of the hydrogens with a deuterium, we'll get something that looks like this. We'll get the deuterium up on one of them, and we'll get a deuterium, a great drawing here, that goes down on the others. And these will be enantiomers, so these will be enantotropic. Here on D, we'll have the same sort of thing. We've got, draw it. If we replace one of the hydrogens with a D, with a deuterium, we'll get one deuterium that's up, and we only have one stereocenter in this compound, and so they're enantiomers of each other. Here we have a nice line of symmetry, so we have a homeotopic.